It's difficult to give a definition of what's electrolyte. These are aqueous solutions. That means solutions that dissolve in water. Aqueous solutions mean solutions that dissolve in water. And they have potential to conduct electricity. They can carry electric current. Okay, so we call them electrolytes. You may want to think about this. Why we call them electrolytes? Because they have ions in them. They have a positively charged ions and a negatively charged ions. When sodium chloride dissolves in water, what are the common ions that are formed there? You don't know. What ions are formed when sodium chloride dissolves in water? There are two ions there, right? What are they? One is the sodium ion, the other is the chloride ion. See, you have two oppositely charged ions. These two oppositely charged ions, they have a potential to carry electric current. So we call them electrolytes. That's the simple definitions of electrolytes. So it's a solution that can conduct electricity. Now, depending on the sensitiveness or depending on the strength of the solution, we can classify electrolytes into strong electrolytes, weak electrolytes, and non-electrolytes. Okay? Don't forget that there are solutions do not conduct electricity, mostly non-ionic compounds. Okay? Sugar dissolves in water, for example. You can mix sugar with water. It forms a solution. But it is not electrolyte because there is no charge there. Why? Sugar is a molecular compound. Sugar is organic compound. It's like C6H12O6, right? There is not any ions there. Whereas sodium chloride dissolves in water. The sodium chloride is electrolyte because it carries ions, positive ion and negative ion. See? So what do we call those solutions? Dissolve in water but do not conduct electricity. They are called what? Non-electrolytes. Non-electrolytes. So now we're going to see about if we have electrolytes. Electrolytes can be strong electrolytes or weak electrolytes. Okay. The definitions of strong electrolyte means that it is a solution that is completely ionized in a solution, completely ionized. In other words, it's a solution that is completely dissociated, not partially, not 75%, but 100% dissociation. So that means the more ions you have, the more it's going to be, a strong electrolyte. Okay? So what are they? All common soluble ionic compounds, acids. What's the name of this acid? Hydrochloric acid. Hydrobromic acid. Chloric acid. Chloric acid. Chloric acid. Nitric acid. Sulfuric acid. Okay. Mostly acids of halogen families are considered to be as a strong electrolyte. Of course, there are some exceptions. Nitric acid and sulfuric acids are in the picture too. But if you think about acids of halogen families, okay, are considered to be as strong electrolytes. Alkali metal hydroxides. Give me an example of alkali metal hydroxides. Alkali metal hydroxides. Sodium hydroxide. Potassium hydroxide, right? Lithium hydroxide. All these are considered to be as strong electrolytes. Why? Because they are completely dissociated, completely ionized in the solution. Okay? We also have weak electrolytes. These solutes that exist in a solution, mostly in the form of molecules, but there is a small fraction in the form of ions. You see, what we can understand from here is that weak electrolytes, still they are electrolytes, but they are not completely dissociated. They are not completely ionized, in other words. They are not completely broken down. There is a molecule and there is ion. There is a molecule and there is ion. Okay? We call these weak electrolytes. Now, for us, how do we know the weak electrolytes? Some common examples are given. What is the formula of this? What is the name of this compound here?
Acetic.
It's acetic acid. Acetic acid comes from where? What kind of ion is this one?
Acetic.
Acetate. Very good. Acetate. What do we know about acetate ion? What's an acetate ion? What is the common characteristics? It's a common feature in acetate ion. It's always soluble in water. Acetate ion is always soluble in water. If you have nitrate ion,
Always soluble.
always soluble in water. If you have acetate ion, it's always soluble in water. Okay. But in terms of acid, acetic acid is a weak acid. It's not a strong acid as like hydrochloric acid or hydrobromic acid or sulfuric acid. And also, acetic acid is a weak electrolyte because it's not completely dissociated in a solution. What is it? What is it here? Comes from carbonate. It's an acid. ATE is changing into an acid. It gives you a name. So see?
Carbonic
Carbonic acid. Carbonic acid. This is just carbonic acid. Just like you have chloric acid. From chlorate, chloric acid. From carbonate you have carbonic acid. From sulfate you have sulfuric acid. From nitrate you have nitric acid. Right? Always when you name acids, you have to use a suffix IC. You have to use a suffix IC. Nitrate, nitric. Sulfate, sulfuric. Chlorate, chloric. Carbonate, carbonic. Well, carbonic acid is a weak acid. And what's the implication of that? The implication of that it's also a weak electrolyte. Why is that? Because there is no complete dissociation. There is no forward reaction. Some of the ions also reorganize themselves, they regroup themselves, they come back. And then you will have molecules and ions. In this case, you don't have molecules, you have only ions when they dissolve in water. There is no backward reaction, there is a forward reaction. Okay? Also, do you remember this acid?
Sulfurous acid.
Which one? Sulfurous acid. Where does sulfurous acid comes from? From sulfuric acid. You know, we had sulfuric acid. Actually, there's a difference between sulfate and sulfite. You remember the difference between sulfate and sulfite? Sulfate and sulfite is that sulfites have one less oxygen than sulfuric acid. Sulfite has one less oxygen than sulfuric acid, okay? But it's not just take away one oxygen, it is also has a characteristic in terms of it is proportic, which is this is weak acid and weak electrolyte, whereas this is a strong electrolyte. Okay? So like carbonic acid, sulfurous acid, acetic acid, hydroxides of transitional metals are not completely dissociated. Okay? Are not completely dissociated. So they are considered to be as they are completely dissociated. They are not completely dissociated. So we call them a weak electrolyte. A strong and okay. Here is a good example. You see, you have two types of reaction. Like for example, hydrochloric acid is a strong electrolyte. It's a strong electrolyte, and you will have a hydrogen ion and a chloride ion. This is like a forward reaction. In terms of a weak electrolyte, you will have a forward and a backward reaction. A forward and a backward reaction. That means the ions are coming together. The ions are coming together, and then it forms a molecule here. In other words, in a solution, you will have ions and molecule. There is no complete dissociation. Here is a forward reaction. Here is a complete dissociation. Here is a forward reaction and a backward reaction. So this is a good example of weak electrolyte. This is a good example of a strong electrolyte. We can see here some examples. Electrolytes, we have positively charged ions and negatively charged ions are completely dissociated here. What is this example illustrated here? What does this example illustrate for you? Is it electrolyte or non-electrolyte? It's non-electrolyte, honestly speaking. It's a non-electrolyte. Because there's no ions here. There's no ions here. I'm sure that you studied this. Did you? Right? Anybody has any questions regarding with this? How to understand this concept? Any questions you have regarding the disability guideline? Because I am asking this, we're going to again go over this in chapter 4, and the rest of the chapters are very important for us to know this. Okay? So again, it's not just for chapter 3. I want you to go over again and study this. Okay? Okay. The next thing I wanted to discuss with types of reaction. We have types of reaction here. What type of reaction is this one from the last definition, the last classifications of reactions? This is called a combustion reaction. It's a combustion reaction. We have C6H12O6 reaction with oxygen and produce carbon dioxide and water. Regardless of any types of reaction, what is important for us? What is important for us?
Balance.
To balance the chemical equation. The equation has to be balanced. Now, here we're going to see about the difference between a formula weight and a molecular weight. Okay? Formula weight. The sum of the atomic weight of the atoms in ionic formula, we call it formula weight. Now, the subscript is not just there, but the subscript is always tells you how many atoms you have. For example, if we wanted to consider the formula weight of H2SO4, the formula weight of H2SO4, and then we have how many atoms of hydrogen we have? We have 2 atoms of hydrogen, 2 times the atomic weight of hydrogen, which is 1. We have sulfur. What is the formula, the atomic weight of sulfur? 32. 32 times 1. So there's only 1 sulfur here. Right? Oxygen, how many oxygen you have here? 4. 4. Multiply 4 by 60. 4 by 60 because the atomic weight of oxygen is 60. Now you add this up and you get 98 mu. That is the atomic, the formula weight of sulfuric acid.
So when you formula weight, like dissolve things, you just like separate it and then you're gonna weight like separate it?
Yes. Let's say if I ask you what is the formula weight of sulfuric acid, you have to add the atomic weight of each. But before doing that, you multiply by the subscripts. If you have subscripts, like formula weight of hydrogen is atomic weight of hydrogen is going to be 2 times 1, which is the atomic weight of hydrogen is 1. Atomic weight of sulfur is 1 times 32. Okay, the numbers will be provided to you on the test. You don't have to remember the numbers, but what you should know is to multiply by their respective subscripts and add them up together. That gives you the formula weight. Okay, the concept is the same for molecular weight as well. We use molecular weight for molecular compounds. That's all. Okay, formula weight. We use formula weight for ionic compounds. Okay, for ions. Formula weight of sodium chloride, for example. There is no any subscript here. What I need to do is the weight of sodium plus the weight of chlorine together. Weight of sodium and chlorine together, and then I get what? 58.5, because sodium is 23, chlorine is 35.5, and that gives me the actual weight of sodium chloride. Okay?
Can you go over and move out?
Yes. Here.
Yeah, but how did you get 23?
23 is the atomic weight of sodium. I found that from the periodic table. It might be 22.9, maybe we can round it to the nearest whole number.
So it's like same thing as formula weight.
It's the same. Well, actually, this is a formula weight.
Oh, okay.
This is a formula weight because sodium chloride is ionic compound. You see, the formula weight is used for ionic substances. Molecular weight is used for molecular substances.
So how you get it is like the same thing, right? Like you just multiply the subscript.
Yes, it is the same thing. It is a matter of terminology. It is a way. I will ask you, what is a molecular weight? Or I will ask you, what is a formula weight? The molecular weight is a reflection of molecular compounds, covalent compounds. The formula weight is a reflection of ionic compounds, that's all, but the concept is the same. The principle is the same. So in a reaction also, we can use the concept of molecular weight and formula weight. Now, you have chemical reaction here. You have CH3OH, methanol, react with oxygen, because this is a combustion process. You get carbon dioxide and water. The equation, of course, has to be balanced, right? How do we interpret this? We interpret this as there are two molecules of methanol, right? The coefficient, two molecules of methanol, reacts with three molecules of oxygen. It generates or it produces two molecules of carbon dioxide plus four molecules of water. Okay, this is the ratio. Okay, it's a balanced equation tells you why we need to balance the chemical equation. It's not just because of the law of conservation of mass. It's not because we have to, but it tells us the amount. This is really the concept. This is a key part for stoichiometry. Stoichiometry means that how much you have on the left-hand side and how much you get on the product side. That's what we need to balance the equation. So every two molecules of methanol reacts with three molecules of oxygen. That guarantees me to have two molecules of carbon dioxide and four molecules of water. That's how the essence of balancing the equation. Okay, if this is reduced, this is going to be reduced. If this is going to be higher, this is going to be higher. That's why we need to balance the equation. Okay, sometimes my question from now on is going to be, Donna, I have two molecules of CH3. I have 5 molecules of oxygen. How many molecules of carbon dioxide do you think I would get? Or how many molecules of water should I give? Such questions will come in. So how do we answer this? We can answer this question if we properly balance the equation. If we properly balance the equation. Now, for a practical purpose, remember when we dealt with the formula weight or the molecular weight, we dealt with the unit was AMU, right? The formula weight of sodium chloride was 58.5 AMU. The formula weight of glucose was 180 AMU in the previous slides, right? But AMU, what is AMU? Atomic mass unit, right? For a practical purpose, we know that atomic mass unit is very, very, very what? Smaller. Smaller, right? Now, you do experiment in the laboratory. Are you dealing with AMU or are you dealing with grams? For a practical purpose, for experimental purpose, for regular labs that we have upstairs, we use grams. We don't use AMU because 1 AMU equals to what? 1.6 times 10 to the power of minus 24, I guess. Minus 24, minus 27 grams, which is very, very small. You can't measure it in your eyes, right? You need to have a special instrument. But grams stands for a scale, stands for a top loading balance we have in the lab. We can measure it, right? So because of the practical purpose, we're going to introduce a molar mass, concept of molar mass. What is molar mass? The mass in grams of 1 mole of a substance. It is numerically equals to the formula weight or the molecular weight of the substance. You see, you have a formula weight. For example, the formula weight of sodium chloride was 58.5 AMU. What will be the molar mass of sodium chloride? The same thing, 58.5 grams. Can you do 58.5 grams in the lab? Of course, you can do 58.5 grams, right? That is the formula weight. Now, what's the difference between the AMU and molar mass? Or in other words, the molar mass of sodium chloride or the formula weight of sodium chloride. The formula weight of sodium chloride is expressed in AMU, whereas the molar mass of sodium chloride is expressed in grams. Numerically, they are the same. What is the difference? The difference is the unit. But for our case, for our purpose, we prefer what?
Right.
Molar mass, gram. Yeah, because we can handle that. We can do grams, right? That also has another significance. You know, I just want to tell you about mole. You may heard mole maybe in the lab, right? 1 mole of a substance. Just think about it. For example, you go to the shop, you go to the store, you buy 1 dozen. 1 dozen eggs. How many eggs you have? 12. 1 case. 1 case of soda. How many sodas you have in 1 case of sodas? 1 case.
6.
1 case is 6. Case?
Depends on what.
Okay, well, a case is 6. Okay, well, there's 24 too, right? You can 24, right? This is what we're using in our daily life. Anyway, I mean, I'm just picking examples right now. One case, 1 dozen, 1 gross. Okay, these are examples, right? This is what you use in your daily life, right? In chemistry, also, we are dealing with atoms, molecules, particles. There are millions, billions, trillions. You can't count them. So there has to be a specific unit to express those huge quantities. That's one of the units is 1 mole. Okay. Experimentally determined result shows that 1 mole of a substance, 1 mole, M-O-L-E, is equivalent to 6.02 times 10 to the power of 23 particles. Just like 1 case is 12. I mean, 1 dozen is 12, or 1 case is 24. 1 mole of anything, 1 mole of water, has 6.02 times 10 to the power of 23 molecules of water. And that is called the Avogadro number, Avogadro's number. Now, I'm pretty much sure you can't count 6.02 times 10 to the power of 23. Assume this is a billion, trillion, it's a large, huge number, right? But we can have a system, for example, 1 mole of a substance equals to the formula weight of that substance. In other words, to make it easier, take sodium chloride. What is the molar mass of sodium chloride? The molar mass of sodium chloride. 58.5 grams, right? The weight of sodium plus the weight of chlorine together, that gives you 58.5 grams. That is the formula weight of sodium chloride, 58.5 grams. Guess what? That is equals to 1 mole. That's 1 mole. Can you do 58.5 grams in the lab?
Yeah.
You can cut 58.5 grams, you can weigh, then you make sure that that's 1 mole. If it is 1 mole, how many particles of sodium chloride you have? 6.02 times 10 to the power of 23 particles of sodium chloride you have. That is the experimentally determined number. Does that make sense? If you have 2 mole, for example, what is 2 mole of sodium chloride equals to? 2 times 58.5. 2 times 58.5. What is 2 times 58.5 equals to in terms of number? 100. I'm sorry? 117, right? Now, how many particles of sodium chloride you have? In 2 moles of sodium chloride.
6.02 times 10.
Yes, you have 12.03 times 10 to the power of 23. We're going to continue this on Friday, okay? Okay? And calculate the formula weight or the molecular weight of this compound. Okay? This is only a slide. So I want you to do this calculation for Friday. It's homework, yes. It's a practice. It's a practice for you.
So we're not giving any data.
Yes. Yes. Yeah.
I
I have graded. I'll bring Friday. It's already. I have changed the grade for you. Okay. And you know, just the time. I'll bring it for you. It's already.